Good morning, doctor. I'm Lim Ching Wan, and now we will proceed to the assignment 1. For assignment 1, part 1, we are required to develop a finite element model of a heat transfer problem using the MATLAB PDE toolbox. Okay, now we need to follow the instruction on the following link to model a heat transfer problem in blocked with cavity using the finite element method. Okay, now after open the link, this is the link lah, okay? Now we proceed to the step 1. In the step 1, we need to open the PDE modeler apps by using the PDE modeler command. So we go to the MATLAB, and this is the MATLAB. And at the command window of the MATLAB, we need to type the PDE modeler inside. Okay, after type the PDE modeler, we actually can see that the PDE modeler apps appear. Okay. Next, we need to draw two rectangles. One is the big rectangle with corner given, and one is the small rectangle also with the corners given. Okay, now we will draw the bigger rectangle first. We will copy this value. Okay, copy. And we paste in the command window of the MATLAB. Okay, we place enter. After we enter, we can see actually the rectangle appear in the PDE modeler. Okay. So next we want to display the grid line with extra text at negative 0.05 and 0.05. So to do this, we need to select the option and grid spacing. And we clear the auto at the x-axis linear spacing here. Okay, now the x-axis extra text is negative 0.05, 0.05. Okay, apply and done. After apply, we can see that these are the interval from negative 0.05 to 0 and 0 to 0.05. Okay, after that, we select the option again and grid. And after the grid selected, and the gray line appear. Okay. Okay, next we need to set the x-axis limit and the y-axis limit. So we go to option again and axis limit. So the axis limit is negative 0.06, negative 0.6 to 0.6, 0.6 to 0.6. Okay, and the y-axis limit is negative 1 to 1. Okay, no change. Okay, so we apply and close. Okay, after apply, we can see the rectangle is like this. Now we proceed to step 5. Step 5, we need to draw the rectangle with corner given. Okay, then we choose the option again and snap. Okay, option and snap. Okay, then we need to draw the rectangle with corner given. So we begins with the corner negative 0.05 and 0.4. So we go to draw and rectangle. Okay, then we can see that the x value and y value here can change when we move our mouse on the axis. Okay, so we begin with the point negative 0.05 and 0.4. So 0.4, negative 0.05, you can see here for the value. Okay, then until the endpoint is negative is 0.05 and negative 0.4. Okay, like this. Okay, we'll give the value right here. Okay, now we drag the small triangle, a small rectangle. Okay, we can see that they are quite accurate lah. Okay, they are very accurate and with small error. Okay. because the option snap is applied, so the snap helps to align any new shapes to the grid line. So next we will model the geometry by entering R1 minus R2 in the set formula field. Okay, in the set formula here, we need R1 minus R2. Okay, just like this. So we go to the step number 7. So 7, we need to check that the applications mode is set to generic scala. We can either see here, or we can go to option applications, and we can see that the generic scala are chosen. Okay. Okay, next we need to specify the boundary. First, we go to boundary and boundary mode. Okay, after boundary mode, we can see the picture in error. Okay. Next, we will go to boundary again and select specified boundary conditions. Okay, boundary condition will appear here. Okay. Then, for convenience, first specify the insulating Neumann boundary condition del U over del N equals to 0 for all boundary. So we need to select all. To select all boundary, so we go to this one, and we go to edit, and then select all. Okay, we can see that all the error are selected. Okay, so we then need to change the new one boundary condition as G equals to 0 and Q equals to 0. Okay. Okay, now we will see the left side of the block. Okay, to set the boundary condition for the left side of the block, we just double click on it. Okay, then it's a directionally, so we press the directionally boundary condition, and we set hash equals to 1 and r equals to 100. Okay. Okay, next we need to specify the Neumann boundary conditions. Del U over del N equals to -10 for the right hand side of the block. Okay, so we double click on the right hand side of the block, then it's Neumann, and then G is -10, and Q is 0. Okay, now done. Okay, our boundary condition are set. Okay, after that, we will specify the coefficient by selecting the PDE. Go to the PDE specification or just clicking the PDE here. Usually I will go to PDE and PDE specifications. Okay. Okay, now we see that the heat equation is a parabolic, so we choose parabolic here. And then specify C equals to 1, A equals to 0, F equals to 0, okay, and D equals to 1. Okay, still nothing happened yet because we just set the value. Now we will need to initialize. Okay, now we need to initialize the mesh first. This is step number 10. We need to select mesh and initialize mesh. Okay, after initialize mesh, we can see that the triangle appear in the big rectangle, but not the small rectangle, because the small rectangle is a cavity. Okay, now we need to refine the mesh again. So we go to mesh again and refine mesh. So more triangle will appear and the triangle becomes smaller. Okay. Now we need to set the initial value to 0 and the solution time to 5 seconds and compute the solution every 0.5 seconds. So to do this, we will go to solve. Okay. and parameters. So in the soft parameter dialog box here, set time to 0, 0 0.5 and 5. 0, 0 0.5 and 5. Okay, and U T naught to be 0, 0. So we said okay. Okay, so nothing happened yet, still. Okay, now we proceed to step 12. We need to go to the PDE by soft, then soft PDE, or just simply click the equals button here. So we go to soft and soft PDE. Okay, after soft PDE, we can see that our plot is like this. Okay. Okay. Now the F solves the heat equation at 11 time from 0 to 5 seconds and display the heat distributions at the end of the time span. So now we need to plot the isothermal lines using the control plot and the heat flux vector fields using the arrow. Okay, and changing the color map to hot. So to do this, we need to go to plot and parameters. Okay, go to plot and parameter. So in these plot selections, we need the color, counter, error, but error need to go to -C grad view. Okay, now we need to change the color map to hot. Okay, so we plot and close. Okay, now we can see that our plot will be like this. Okay, plot will be like this, just same as this, just same, look same lah for this lah, from the look same from the example. Okay, next we proceed to the next step. Now we want to use the animator plot to visualize the, okay, this is the plot. Okay, we want to use an animator plot to visualize the dynamic behavior of the temperature. So we go to plot again, and parameter again. So we now select the animations here. So we plot again. We can see that the heat transfer is very fast. Very fast, okay. Heat transfer is very fast. Okay. Okay, now we will look at the step 15. From the previous time setting, we can see that our animator plot, the process is very quickly. This is because the temperature in the block rise very quickly. Okay, so to improve the animation and focus on the first second, we will change the list of time to the MATLAB expressions, log space -2, 0 0.5, and 20. Okay, to do this, we will select soft and we go to parameter. Now we will change this to log space -2, 0 0.5, 20. Okay, we select OK. Then we plot again. We select OK. Then we plot again. So we plot. Okay, now we can see that the process of the heat transfer is become slower. So we can have a clearer visions in this animation plot. Okay, from the right hand side of the block, we can see that the heat escape from the right hand side of the block. Okay, this is because the Neumann boundary condition we set at negative, and the flux we also set as the heat flux we also set as negative C grad U. Okay, if we set the Neumann boundary condition at 0, we can see that at the top and the bottom part, no heat enter and no heat out from the block. Okay, now we'll proceed to the step 16. We can explore the solution by varying the parameter of the model and plotting the result. So I will changing the heat capacity coefficient D and the right boundary to see how this parameter affects the heat distribution. Okay, now let's go to the PDE specification. So now I will change my D to 10. See what will happen if D equals to 10. Okay, so we plot parameter and plot. We see the animation plot. Okay, now we can see that the heat transfer is become slower if compared to D equals to 1. Okay. Now, let us change the D value again. Now this time we change to a bigger value like 50. Okay, so we change D equals to 50. So click OK. And we again plot the solutions. Okay, from this animation plot, we can see clearly that the speed of the heat transfer becomes more slower. Okay, so we can conclude that if we increase the heat capacity coefficient D, increase the value of D, we can see that the animation plot shows that the speed of the heat transfer will be slower. Okay. Okay, now it's our D. So now we will change our D back to 1 first, and we change the right boundary and see what will happen. So previously it's 1. Okay. So we go to the boundary and boundary mode. Now this is the boundary mode. So we need to change the right side, the boundary of the right side of the block. So let's see. Okay, for the G value, instead of negative 10, I want to change to a positive number 10. So we click OK, and we go to plot and plot parameter. We want the animation plot also, so we plot. Okay, now we can see clearly that the heat transfer from the left hand side to the right hand side, and then to the right hand side and back to the left hand side. At the right hand side, the heat does not escape. The heat not only does not escape from the right hand side block, from the right hand side of the block, but the heat also transfer back to the left hand side. This is because the Neumann boundary conditions we set for the right hand side, or we can say we set the G value as the positive value. Okay, now let's see if the value become negative 100. Okay, what will happen? So click OK, and then we click plot and parameter, yeah, animations. Okay, then we plot. Okay, from the animations, we can see that the heat transfer will stop until one limit. Yeah, the heat transfer will stop until a limit. Okay, and at the right hand side, the heat also escape since we have the negative value for G. Okay, So that's all for me. Thank you.